into that LCA approach as well to their different designs. So I would like to make a start to the webinar proper. We have a packed agenda today, so we will not spend too much time and more in the introduction. Today we have 5 projects, as I mentioned to you earlier, all part of the EnlightEVs cluster. We have the ALMA project, which we'll be presenting first, followed by Fatigue for Light, Flamingo, Revolution, and Levies. To start off with, I would like to introduce you to the ALMA project, who will be presented by Ms. Vanessa Ventosinos from CTAG, who will also be joined by Pascal Lorenzini from ArcelorMittal to talk about materials, and Tom Ligthart, who will then also highlight on how we've done LCA to make sure that all of our designs are actually improving sustainability. So without further ado, I would like to introduce to you Ms. Vanessa Ventosinos.
Thank you, Jose. I'm going to share my screen. Let me know if it works properly. Okay, can you see my screen?
Yes.
Great. So thank you very much for this opportunity to present ALMA project. The main goal of ALMA, in fact, is rethinking the electric vehicle structure in terms of sustainability. So to do so, we have adopted like 2 strategies. The first of all is lightweighting. It's certainly related with the energy consumption of the whole vehicle, but we have approached this lightweighting from an eco-design perspective. So we have introduced to the design not only this lightweighting potential, but also all the life cycle assessment, as previously mentioned in the introduction, in fact. And the second strategy that we have following is to promote the reuse and recycling at the end of life by promoting the sorting of all the parts, using the bondable adhesives and the bondable unions that promote this sorting at the end of life, and the monitoring of the state of each part at the end of life. So in the consortium, well, CTAG is the coordinator, but we have also a TNO who developed the LCA and LCC tool, BEVSIM, that is going to be explained later. Fraunhofer for modeling, for validation, ArcelorMittal and BATS for new materials and innovative materials. Pascal from Arcelor is going to explain a bit about that. So we have chosen as advanced materials steels and SMC based on glass fiber reinforcement, not only because of their performances, but also because the cost effectiveness of such solutions, because it's easiest to bring this innovation into the market, into the mass market, if you are considering also the costs. So today, in my presentation, I'm going to be focused on the design, the eco-design approach that we have followed. So our motto was to choose the best material in the best location and to take profit of these new materials in terms of geometries and functionalities, changing the whole design of the structure. Okay. So in a lot of applications and a lot of systems and subsystems, steel was the only option because of the very high and demanding crash performances in different systems. But in other ones, there was a doubt about which option can be the most suitable in terms of what to choose: SMC composites, steels. And this system were the dash panel, the rear floor panel, the battery lid, and the rear tray. So to choose the best option, we have followed an assessment, an eco-design assessment that weighs different parameters. The first parameter was to assess the weight saving potential of using each material for each of these subsystems. The other parameter was the circularity. So if the components can be recyclable or not, or easily disassembled at the end of life or not. So we have also weighted this parameter. We have included also as a key factor the number of references saved. Because we have changed the design. So in using these very advanced materials, we were able to implement different functions in the same part, which is not only suitable for sustainability point of view, but also for costs. And as I mentioned, our goal is to bring all this innovation into the mass market. So it's a key factor. And talking about that, another key factor to bring the innovations into the market is the compatibility with the current assembly lines in the OEMs, so that these new concepts, these new materials cannot change radically the assembly line that we have today, in order to be sure that these innovations can be adopted as soon as possible. So this was an assessment in a sense a bit qualitative, but we have also combined this assessment with LCA assessment, which was more quantitative. And to do so, we have used a tool that was specifically developed for ALMA project. Our colleague from TNO, Tom, is going to explain it a bit. So we have combined both approach in order to choose the best material for each of these subsystems. And we have come to this conclusion that the structural SMC was the best option for the battery cover and the dash panel. And we choose different grades of advanced steels for other parts that allow us to rethink, for example, the H-frame and the door panels to have a lighter and more performance structures. After this redesigning, of course, we follow an approach to validate that this new concept works in terms of crash. To do so, we have followed a Kai crash validation, so it's a simulation with 5 different scenarios of crash, and we reach a fully validated design, which reach at 23% of lightweighting compared to the baseline. We are quite happy with this result because our initial goal was 20%, so we have reached our goal in fact. So this is just our first introduction in ALMA in terms of eco-design, and now I think that our colleague Pascal from Marcelo is going to explain a bit about the advanced steels and materials. Pascal, I don't know.
Yes, okay. Yeah. Thanks, Vanessa, for giving me the floor. So I'm going to share my presentation. So just confirm me, you see it well?
It looks good.
Okay. Okay, so just some words about our company, ArcelorMittal. We are the leading steel supplier for automotive, as we provide around 70% of the global worldwide automotive market with the widest product portfolio. And we rely on a global network of R&D labs, both in several European countries, North America, Brazil, and so on. And in our strategy, we are strongly involved in relationships with car makers on co-design activities. So what about our involvement in ALMA project? We support the car maker Ford and CTAG in the implementation of new steels in the car design. So up to the production of demonstrators of the solutions. And Vanessa told some words on quite, let's say, already well-known solutions, steel solutions for those who are involved in car light weftings, such as the door rings made of new steel rails, or the H-frame made of press-hardened steels. And specifically in the field of ALMA project, we developed new steels with advanced properties to optimize the light wefting, which was shown by Vanessa previously. So I'm going to highlight now these kind of steels, which are sorted in 3 categories, depending on the kind of parts on which they can bring lightning. Firstly, a very high string steel grade called 40form S1270. So 1270, why? Because it's the minimum value of its tensile strength. And so it's dedicated to the lightening of structural parts. So, shortly speaking, it's a medium manganese trip steel with a quench and partition microstructure. And regarding its in-use properties, we validated its formability, which is close to that of dual phase 780, though the mechanical properties are far more high. And of course, it leads to optimal crush performance. This is the main goal for structural parts, together with an ability to be spot welded following conventional process. So that's one I want to figure out by saying without any post welding head treatment, which would make the process longer, and so it's not what we want to do, of course. It exhibits a good resistance to let's say what is called ALMAs. So this is a very important problem that on some grades OEMs are facing. And it has a good resistance to delayed fracture also due to its low erosion and brittlement. So here, just as a matter of illustration, you see what are the foreseen applications. So in the frame of ALMA project, we obtained a weight reduction on this kind of parts around 30%. And these parts are mainly reinforcements, crush boxes, roof cross members, as you can see on this picture. So let's now come to a second kind of steel, which is a laminate. With a core layer of thermoplastic polyamide. And this is sandwiched between 2 very thin steel sheets, which are interstitial-free steels for durability. The fact is that due to this specific structure, we can reach a very interesting wave saving around 40% at iso stiffness, bending stiffness, and with a good formability of the laminate. These thermoplastics are compatible with the e-coat process and are also self-adherent to the steel. So this is very interesting in terms of processability. So contrary to the 1270 grade, the objective is to target non-visible panels, but without structural functions this time. So like floor panels, hood inner or trunk inner. You have, for instance, an illustration of how a hood inner can be formed without any crack using this steel laminate. And in the frame of the ALMA project, we developed press technology aiming at delivering large samples in view of demonstrators. And so the third example of steel, which was took on board in the frame of ALMA project, is a low density steel. The objective of which is to lighten the outer panel this time. So you see that the goals of each our steel grades are complementary. And what's the technical value of this solution? Thanks to the addition of around 6% of aluminium in the metallurgy, we reach a density reduction to 7.2 instead of 7.8. And this kind of steel has an excellent dent resistance, which is a key properties for outer panel, with the same yield strength as Dualfast 600. And this kind of a concept enables to adapt the range of ductility achievable through the adaptation of the ratio of ferrite versus austenite in the microstructure, because this is a duplex microstructure. That's why it's called a duplex concept. And main results of our involvement in the project is, on the first hand, the adjustment of the target to the spec of the outer panels in terms of uniform elongation to be reached. The adaptation of the hot dip coatability process to the high aluminium and manganese contents of this kind of steel. And so the verification of formability, which is compatible with the specification of today thinnest outer panels made in the best of class steel grade for this kind of uses, which is Dualfast 500. And again, as previously on the steel laminate slide, you can see the kind of panels which are targeted, so doors and hood outers, trunk outers, and the saving potential which was calculated in the frame of ALMA project. So that's all for my presentation. Thanks for attending to it.
Thank you, Pascal. Now we have Tom Ligthart from TNO.
Yeah,
Talk about LCA.
I'll take over and try to keep it short. Let's see, and now I have to go to the, sorry, lost the mouse. Yeah, I think you're able to see it now.
Yes.
Yeah, so the BEVSIM tool made by a team of colleagues. Give a very short presentation on that. So it's an LCC LCA tool designed for non-LCA experts, and with the ability to compare design alternatives. And as you see, it has been applied in BEVSIM, and it gives, well, fast LCA results. Then it's, yeah, well, of course, with a LCA part and LCC, but also a circularity indicator in it, and including the full life cycle from the materials, processes, use phase, also the end of life, and you can apply different scenarios for especially for the end of life, but also for the electric vehicle. Select different electricity scenarios. You can edit a full car in BEVSIM, but also do it on the level of subsystems or even parts. And with that, you have a large freedom to make your own comparisons. You select a user design and can compare that to two different references. And so immediately see what your design choices have an effect. We, as said, full life cycle, so material, the processes, assembly processes, and very important, of course, the use phase. In green, you see the internal combustion engine, and in blue, the battery electric vehicle. And it's clear that especially the battery, you have a larger impact of the battery, of the materials, but it is paid out in the use phase. There you see that the internal combustion engine, a petrol car in this instance, has a much higher impact, and overall that gives the battery electric vehicle a better performance. You can also do the here you see the global warming potential, but also other impact categories from recipe can be shown, and the life cycle costing results can be shown. I will not show it. And we have the material circularity indicator. So that's an indication on how your circularity of your design is working. The closing remarks, it's on the full life cycle that you can do the studies. And because it's much simpler, but still offers a full LCA, you have significant savings in time and efforts. And still you can put LCA in directly into your design process. The BEVSIM tool also has the advantage that it's consistent, and you can have access if you send me an email. There is a small fee based on it, but please, contact me if you want to have a demonstration or access. So I hope I gained some time with this presentation. And as said, thanks for your attention, and feel free to contact me to know more about the BEVSIM tool.